In this work, we explored the characteristics of multiple power and energy sensors exposed for AMD GPU and APU exascale nodes, specifically Frontier and Portage. The sensor data passes through 3 asynchronous stages. The sensor hardware produces the data at its own pace, the operating system driver receives and publishes the values, and the instrumentation tool reads them from the operating system. Each stage has its own update cadence, and the lag between the first and last stages sets the bounds for what we can attribute. Every sensor also has 3 time constants: a delay before it starts responding to the GPU activity, a response time as it rises to steady state, and a fall time as it returns to idle. The confidence window is the interval where the reported value matches the real signal. Outside that, the measurement is dominated by transitions. We applied this model to 2 sensors on each machine. The ROCm SMI driver exposes 1 millisecond power and energy readings from an on-chip sensor. The power is averaged before it's exposed to the user, but the energy counter is not filtered. The off-chip Cray PM power and energy readings refresh every 100 milliseconds. They report raw values and are accurate to within 5 to 10%. Next, we derive power from ROCm SMI's energy counter. This bypasses the firmware's filtering and allows us to recover instantaneous power at millisecond timescales. On a workload with square wave-like activity, the average ROCm SMI power is highly smoothed. Cray PM delivers instant but coarse-grained readings at the 100 millisecond cadence. The derived power, however, closely follows the true signal at millisecond level resolution. Then we collected traces from 3 HPC applications and measured the power and energy. On 128 Frontier nodes, ROC-HPL ran at about 80 seconds at 180 kilojoules per node. Switching to mixed precision brought the runtime down to about 30 seconds and the node energy down by 79%. When looking at the differences in instantaneous power draw, we see little change. The energy savings mainly come from shorter time to solution. Finally, the model lets us quantify the timescales where each sensor can confidently attribute power to the workload activity. When application events have durations that exceed these thresholds, the measurements accurately track the shape and impact of the workload's activity on the power without any loss in fidelity. Below them, aliasing begins to merge the peaks and troughs of the workload activity reflected in the power metrics. That covers the 5 contributions: the model, documenting the sensor update behaviors on both clusters, deriving power from ROCm SMI's energy counters to obtain better measurements, collecting these metrics for application traces, and the aliasing analysis that bounds confident attribution.